Welcome to this tutorial on normalizing flow, which is a new type of probabilistic generative model. The pictures that you see here were created using a type of normalizing flow model called GLOW. Now, what distinguishes normalizing flows from other generative models is that not only they are generative, but also have the capabilities to do exact density estimation. The purpose of this tutorial is to explain its motivations and goals, as well as the main ideas that are at the core of any type of normalizing flow model. I will explain the necessary fundamentals to build your intuition and go over the essential underlying mathematics. Hopefully, once you have these foundations, then understanding the research in this area should become easier. The two main challenges that normalizing flows aim to address are as follows. If I have a sample, what are the parameters of the distribution that it belongs to? And can I generate new data points from a given distribution? Let's take few minutes to appreciate these challenges in a bit more detail. The first one is about the distribution from which the sample came. I believe before learning how or what, we should always ask why. In this case, why would we want to know to which distribution my data belongs? There are two primary reasons that I can provide here, and they are exploration and decision making. Exploration means that once I have a way to get the shape and the distribution of the data, it not only tells me about a particular data point, but presents the full picture as well. This big picture then becomes instrumental in answering variety of questions. As an example, I could now learn how data points are related to each other. Do I have many peaks in my distribution? How the density changes based on my modification to the process behind it. The next benefit is the property of being able to compute the uncertainty associated with your data points. This is what helps in decision making. For example, thanks to uncertainty, you can now reason and ask yourself questions such as, am I encountering a data point that has an extremely low probability of happening? Maybe I should not take any action if it is the case, or maybe even raise an alert in my system. Is the probability for the result within the configured threshold? So you see, these two benefits are largely missing from the traditional machine learning. The traditional machine learning algorithms do have elements that may give you a notion of a score associated with the predictions, but those algorithms are not necessarily designed with exact density computations in mind and hence have some limitations. So, problems that I have described so far are addressed by a family of algorithms that are called density estimation techniques. These techniques broadly fall into two categories: non-parametric methods and parametric methods. In this tutorial, we are focusing only on the parametric method called normalizing flows. Now, the density estimation is a very well recognized area within statistics and machine learning. This means that many algorithms do already exist, and it is important to appreciate what are some of the challenges they have. The challenges in the area of density estimation primarily stems from the fact that we are now in big data realm. The data is very high dimensional, and moreover, there is a correlation and covariance in the data that we deal with. These challenges then morph into the difficulties in designing robust algorithms and the requirement of computational time during training and prediction. You may think that we have big data, but we also have now powerful computers. And I would not completely disagree with that fact. But you must appreciate that a significant amount of functionality is executed on devices that live at edges. And those embedded devices are not necessarily rich in resources. So, therefore, the low computational requirements are very real for any industrial solution. Let's look at the other aspect, which is about generating new data points from the given distribution. Again, we would want to know why it is important to sample. There are three primary reasons that I can give you, and they are to simplify compute, dealing with unobserved variables, and need of synthetic data. Let's see them one by one. An example of simplifying the compute is related to the estimation of posterior distribution. Here I am showing you the Bayes rule. Bayes rule or Bayes theorem is very elegant, and while formulating the posterior distribution using this rule is quite simple and intuitive, it is a computation that unfortunately is intractable in high dimensional space. The culprit that makes it intractable is the integral, an integral that operates on high dimensional data and appears in the denominator of the Bayes rule. So traditionally, we get around this intractability either by using sampling methods such as MCMC or by using variational inference algorithms. Another area related to this goal of simplifying compute is the computation of expectation of a random variable. Now, expectation is the central tendency of a random variable. On the right hand side of this equation is shown the expected form of expectation, which is an integral in a high dimensional space, and we have issues of intractability. As you can see, in terms of challenge, this is not very different from the estimation of posterior that I described earlier. One way we get around the integral problem is with the help of law of large numbers. This law states that if we can sample from the target density function, which is p in this case, you may get to the expectation by simply doing the average of the samples from the distribution p. The trick here is sampling, that is, you should be able to sample from p. But reality is that most of the distributions of interest, sampling is sometimes not even possible, let alone easy or computationally efficient. And hence we have this challenge of simplifying the compute. The second use case is related to the case of unobserved variables. There is a type of a model called latent variable model where we assume the presence of unobserved variables. These unobserved variables are called latent variables. The Bayes rule and expectations are again used in the algorithms for these types of models as well. So you again have a need for sampling. Traditionally, these algorithms assume a simple distribution for latent variable model so that we can sample. But this assumption comes at the cost of not selecting an appropriate distribution. As a concrete example, one modern algorithm that is used for latent variable models is the variational autoencoder. And very much like in other variational inference algorithms, here we assume a simpler distribution for both latent and observed variables because of the challenges in sampling. Finally, sampling is helpful for synthetic data as well. We all know that collecting and labeling data sets are costly, but even more important are the other issues, such as privacy aspects. You see, we are not very far from the times when the rules and regulations on privacy aspects related to machine learning data sets and algorithms will be enforced. And indeed, they should be enforced. So if I can easily generate synthetic data from a sophisticated distribution, it would prove to be helpful to train deep learning based models. So this is another utility that we desire. And very much like that of density estimation, there is a huge body of work done on sampling techniques as well. There are plenty of algorithms that one can use. Some of the traditional ones are inverse CDF transform, rejection sampling, and importance sampling. However, these techniques are good only for low dimensional spaces and require that you do have a way of computing the density as well. There is a family of sampling methods called MCMC, that stands for Markov chain Monte Carlo, that can work on high dimensional data but are not computationally efficient, at least not computationally efficient where you have real time requirements. In other words, most of the problems that we saw in the context of density estimation apply to the sampling aspect as well. Same issues: big data, high dimensionality, and dependence. Before I start to explain the big idea behind normalizing flows that aim to address density estimation and sampling challenges, I wanted to say a few words about two famous types of networks, as both of them seem to give an impression that they do density estimation as well as are easy to sample from. The first one is GAN, generative adversarial networks. Now, GANs are good at sampling, and this also means that indirectly they have learned the distribution of the data. But you must know that they are not doing the density estimation part explicitly. They cannot score out of distribution data. Maybe with simple modification, they can output the score associated with the sample that they are generating, but not necessarily to the out of distribution data. Main point here is that first and foremost, they are not designed to evaluate densities. Hence, these are better called deep generative models and are not necessarily density estimators. I already talked briefly about VAE. VAE is an algorithm to find and incorporate the latent variables. They do have an explicit density estimation part, both for latent variables as well as for the data, that is the observed variable part. The problem is that they do require some assumptions on the distribution of these variables. I spoke about it a little bit earlier as well. More specifically, the assumed distribution should be simple enough to do sampling. And it is also preferred to have reparameterizable distributions so that we can have low variance during gradient update. Again, loss function is not the maximum likelihood estimation, but a proxy method called evidence lower bound. I hope that the motivations of having a tractable density estimation and sampling techniques should be clear by now. We will now take the baby steps to get to the big idea behind normalizing flow. The first baby step is the simplest but most important. Let me take you back to middle school and ask you to solve an equation like this. Essentially, you are asked to find the roots of this equation. Clearly, the polynomial of degree 6 is a bit intimidating one, but a very careful observation should help us out. We can rewrite the equation in a different way, something like this. And once we do this, we can again rewrite it as a polynomial of degree 2 by substituting x cubed with a new variable called u. Essentially, we have changed our variable. Now, all we see is a quadratic equation which we know how to solve. I will get two roots, 1 and 8. But then these roots are valid only if my variable is u and not x. To get the roots of x is not difficult either. I do know the relationship between x and u, and using that I can figure out the roots for x as well. This is called change of variable. It's very simple, it's elegant, and it's powerful. I must say that this simple concept teaches us that quite often a little change of perspective helps us solve big challenges. It is true in life and it is true in science as well. So, the question we should be asking ourselves now is if we can apply this type of a concept to do density estimation and sampling from very complex data distributions. And when I say same concept, it means change of variable. The difference, however, is that the variables for us when it comes to do density estimation and sampling are random variables. A random variable is a variable that has a probability distribution. That is, each state has an associated probability. Let's see it with the help of few pictures, and we also are going to connect it to our polynomial example as well, so as to have the intuition alive. Here I am showing an example of a distribution of 2D data. The parts that are shining are the places of high density and the rest are low density areas. Unfortunately, I can neither sample from this distribution nor can I compute densities if you give me an observation. And just for the sake of making analogy, this is like our polynomial of degree 6 problem. I'm going to call this type of difficult distribution a sophisticated distribution or a target distribution. Now I am showing you another distribution. This is again two-dimensional, but this time I know how to sample from it as well as compute density if you give me an observation that came from this distribution. Reason I can do both the task is because this picture is showing the histogram of 2D standard normal distribution where the dimensions have no covariance. Again, just for the sake of analogy, this is our polynomial of degree 2 where we had a variable u instead of x. I'm going to call this simple distribution or the base distribution. Now I have put both the target distribution and the base distribution side by side. Let's say our first task is to compute the density of this interval or the area. I've already told you that I do not know how to do it from this target distribution. Now, taking inspiration from the change of variable technique, maybe I should use the base distribution, that is the 2D standard normal, to compute the density. In order to do so, I must first transform my points or interval in such a way that they would be valid in the 2D standard normal distribution. I'm going to call this transformation G. I would then compute the density, but this density would be valid only for the transformed interval and not the original interval. Remember, when we found the roots 1 and 8, they were with respect to u and not x, and then we computed them for x because we knew the relationship between x and u. This means that somehow we need to adjust the density such that it becomes valid for the original data points or the interval. In the case of polynomial, the relationship between x and u was straightforward. Here, the relationship between these two distributions is somehow determined by this transformation function called g. We'll talk about it soon, but hopefully you are able to see that we are indeed applying the change of variable concept here. Let's consider the other task as well, which is about sampling from this distribution. Again, I cannot sample from this sophisticated distribution, but for sure I can sample from the 2D standard normal. However, I need to then transform. So I got the sample from the 2D normal, but that sample is valid only for the 2D normal distribution. And in order to make it valid for my sophisticated distribution, I need to transform it. The transformed samples then would appear as if they came from the target distribution, which is here shown using a function f. You should start to think if there is a relationship between g and this function f that I am showing you here. Since the idea of change of variable is at the very heart of normalizing flow, I would like to still one more time summarize it so that we are very clear with it. So for density estimation, 2 steps. First is that I need to somehow transform my data from the target distribution so as to make it valid for the base distribution. Making it valid is necessary because that's the only way I would be able to compute the density using the base distribution And then I need to somehow adjust this density such that it becomes valid for the data from the target distribution. Steps for the sampling are somewhat similar, but just in the opposite direction. Here, the first step is to sample using the Bayes distribution and then somehow transform these samples so that they appear to have been generated from the target sophisticated distribution. So the two main aspects to note here are transformation functions and the density adjustment. We saw f and g as the example of the transformation in the previous slides. Now we are at a point where we should now understand the essential mathematics that can help us do these transformations and the adjustment of the density. What I will do is that I will explain the mathematics behind it using a simple example, and then we will generalize from that simple example to a higher dimensional space as well as using more sophisticated type of transformation functions. Here I'm showing you a uniform distribution. The support for this instance of uniform distribution is 0, 1, which is also the more natural support for the uniform distributions. And since this is a uniform distribution, all the samples are equally likely. I'm going to treat this uniform distribution as the Bayes distribution, the one from which we can sample as well as do density estimation. Now I take this uniform distribution and transform all its samples as per this function. It's a very simple linear function, and all it is doing some scaling and shifting. And this is how the transformed density function would look like, which I'm calling again our sophisticated distribution. But as you can see that this is still a simple distribution, but for the sake of our exercise, I'm going to assume that it is a sophisticated distribution from which I can neither sample nor do density estimation. What you want to appreciate here is that as per the property of density function, the total area should still amount to 1. And it should be clear from this figure as well. If you look into the Bayes distribution, the area is 1, which is very, very clear. In the sophisticated distribution, you can notice that the height has now changed to half and the width is 2. So half multiplied by 2 is going to still give you 1. That said, if I pick a small interval in the Bayes distribution, and when it went through the transformation because of this shifting and scaling, the corresponding stuff in the sophisticated distribution indeed got changed. So here dz is the small interval in the Bayes distribution, and the corresponding one in the sophisticated distribution is indicated using dx. So if you want to compute the area that is shown with the help of dz and dx, you would see that the areas in these two figures, in these two distributions, are not the same. Now again, I'm going to use the law of total probability to establish an algebraic relationship between the Bayes and the sophisticated distributions. What I have done is that I have simply put both the areas as an equality. So the area under the density function for the PZ and the area under the density function for the QX. I can then drop the integrals from these two, from both left hand side and the right hand side. And finally, I am able to express the Q, which is a sophisticated distribution, as the function of the Bayes distribution. All that I have done is that I have moved the Q to the left hand side and the P to the right hand side. And similar adjustment for the dz over dx fraction. Let me make some space for further simplifications and derivations from this point onwards. If you recall, in the previous slides, I had mentioned that we could use the Bayes distribution to compute density, but we must then adjust it. This part in this relationship is the adjustment part that I mentioned earlier. I'm calling it the correction part from now onwards. And with just this simple relationship, we are in good shape. Especially if we know Z, we can compute the correct density. The issue is when we do not have access to Z and we only have X available to us. Imagine the case that when you got some data and you want to find its probability, which means that you only have X. Do not get anchored by the example that I showed you where indeed we had Z and then we were transforming. Now imagine a case that you got X from somewhere else. But in order to do the density computation, you need a Z. So this is why it is important now for us that we find Z from our X. Essentially, we need the inverse function that can take us from X to Z. In this problem, it is very easy to do. As you can see, we can very easily get Z from X because our transformation function is super simple. So now we have all that we need to compute the density even if we are using X. We invert X to get Z, compute the probability of Z using P, which is our base distribution, and then multiply it with our correction part. Let's take care of one more aspect. When we deal with numbers in machine learning, it is quite possible that they are very small numbers and our computer may round them to zero if we are multiplying these two small numbers. And the remedy for that is very simple. You see it all the time, which is that we work on a log scale. Logs have the superpower to convert multiplication into addition and division into subtraction, and that's what is happening here. So here I have the log of the Q, and you saw that the multiplication got changed into the addition. There is one last modification that we want to do here as well, which is that even though we are interested in the correction part, we are interested in the absolute value of the correction part. You see, what could have happened was that our transformation might have simply flipped the base distribution, and then you would end up getting a negative sign. And while geometrically it is okay, this is not applicable to probabilities because probabilities are going to be positive. And hence we are taking an absolute of the correction part here, the dz over dx. This equation that I have shown you here can also be written a bit differently. So here you see that instead of a plus, there is a negative sign. And the reason it is there is because I have flipped the ratio. Now in this one, the dx is in the numerator. And both of these notations are there. And this is the reason I wanted to just simply make you aware of it. As you can see that we have achieved density estimation for single variate random variable using the principles of change of variable. Sampling is also not that difficult. As a matter of fact, much simpler than density estimation. All we need to do is to sample from our base distribution and then simply transform it. So here in our simple example, it is just scaling and shifting. The thought that must bother you now is that we have solved it for univariate distribution, but could we apply this concept to high dimensional space? And even more importantly, what if the transformations are nonlinear? What kind of mathematics that is available to us in that case? The good news is that indeed we can apply the concept of change of variable in more or less the same way to high dimensional data and when using nonlinear transformations. There are, however, few more things to know, and these are listed here on the slide. Essentially, the adjustment factor that we had for the density estimation is going to be different in the high dimensional and the nonlinear space. There, the adjustment factor will be given by the determinant of the Jacobian of the transformation matrix. It's quite mouthful to say it. And if you do not know what Jacobian is and or what a determinant represents, then unfortunately it will be difficult to see how they are applied to compute that adjustment factor. Therefore, I am recommending a short list of tutorials at Khan Academy that explain these concepts better than I could. These tutorials were made by 3 Blue 1 Brown, the famous YouTuber, as part of his course on calculus at Khan Academy. So this is my humble recommendation that please go through these tutorials if you have some gray areas and or doubts related to Jacobian and determinant and multivariate calculus. Maybe you already knew the determinant and Jacobian, or maybe you took my suggestion to go to the Khan Academy. In either case, here is a small checkpoint and see if you can explain to yourself what all this means. And if not, please go back to Khan Academy and or write your questions and doubts in the comments, and I will try my best to help. Essentially, you should be able to see that since linear algebra demands linear problems or equations, when we have non-linear functions or curves, then we need to operate on tiny portions of functions so as to keep things linear. This is what the course teaches you, that you ought to find the linearity. That's the notion behind local linearity. And Jacobian is a matrix that records the partial derivatives of all variables around a small point. And what is a matrix? A matrix is nothing but a transformation function that squishes and expands space. The big question then is, how do you find out how much space was squished and expanded? And this is what the determinant tells you. Remember that in our problem for the change in the probability, it is akin to the squishing and the expanding of the space. So in the multidimensional case and in the nonlinear case, it is the determinant that is going to give us that factor, that adjustment factor for our computed density. Moving on with an assumption that you do understand these concepts. We can now reason that in high dimensional space and when using nonlinear functions, the correction part, which is basically about the adjustment for squishing and expanding probability space, is given by the determinant of the Jacobian. This all being said, we are now ready to write our density equation for the high dimensional space as well. And here it goes. As you can see that not much has changed as such from our univariate case. The first term still remains the same. It is the second term, the correction part or the adjustment to our computed density, that has changed and is now relying on the determinant of the Jacobian matrix. So that's the only change. Now, even though we still need to talk about some more challenges and their respective remedies, we are at a point where we can try to formulate the first version of our definition of normalizing flows. And here is how it goes. A normalizing flow is a transformation of a simple probability distribution into a more complex distribution using invertible and differential mapping. Invertible because we need the inverse function to go from sophisticated distribution to base distribution, because we can only compute the probability on the sample that is valid for the base distribution. Differential because we need derivatives that are then put in a matrix called Jacobian in a high dimensional case, and we then compute the determinant that acts as our adjustment factor for the densities. Now this definition is correct. This is good definition, but it is not complete yet. And in order to complete it, we need to see few other aspects as well. These other aspects are about the challenges that we should be able to identify in our equation. Give it a pause here and see if you can think about some of the problems that are present here. Well, one very simple problem to note is the computation of the inverse itself. Inverses are difficult in general and they become even more difficult when we are in a high dimensional space. Second one is related to the computational aspects of determinants. The worst case big O for determinant of a matrix is cubic in nature. So if we have a big complex function that uses high dimensional data, we will have all these kind of challenges. The big question here is that what do we do when we have a big monolithic problem? Well, we quite often divide the big monolithic problem into small parts, solve these parts independently, and then combine the results. We will adopt the same strategy here as well. That is, instead of one big complex function, maybe we will have less complex but invertible functions. And it is the combination of those complex yet invertible functions that would help us go from the simple base distribution to a sophisticated target distribution and then back again to perform the density estimation. So we can go both ways, forward and reverse. In order to understand this concept, let's see some related notations as well. The first concept is about the function composition and its impact on its inverses and determinants. We use the following notation for function composition. What is important to pay attention in this notation is the order of the function evaluation. It happens from right to left, which means that this f1 is going to be evaluated first. The output of f1 will go as an input to the function 2, which is f2, and fn will be the one that will be evaluated last. The good news is that the composition of invertible functions is itself invertible. So this is another. Let's look at the inverse part as well. Here, first I am going to use a different symbol, that is G, to indicate the inverse of a function. Very much like for the forward functions, I would express or compose them using this notation. Note the location of G1, which is the inverse of F1, is different, and it should make sense why G1 is at the start, because the first inverse function that is going to be evaluated will be Gn, because Gn is the inverse of Fn. So now we are going back to the base distribution, which means this is evaluated first and this is evaluated last. Since we now have multiple invertible functions instead of one big function, we need to see what happens to the determinants as well. And this is not difficult either. We can simply compute the determinant at each step and then multiply it. This is what is shown by this equation. So as you saw in previous slides as well, you would be computing the Jacobian, which you compute with the help of the inverse function, and then you take simply the determinant of the absolute value. Now in this case it's a multiplication, and if you recall, I told you that in machine learning we do not like multiplications, and as such in mathematics, in anything that deals with small numbers, we do not like to do multiplications. So we must think in terms of log of determinant here. which is what is shown here. So the moment I do the log on the left hand side and the right hand side, my multiplications get converted into the addition. So we are at a point where we are now ready to write a more complete formulation for our density estimation. So here still I'm showing you the multivariate part which we had earlier. Here you see there is only one function that is shown. Now the change that we are making here is that we are now using not just one function but rather a sequence of functions. And hence you see that there is a summation notation which goes from 1 to n. N essentially is indicating the number of functions in our composition change, where each function is an analytically invertible function. Based on all this, you can see that with the help of these sequence of invertible and differential mappings, we can perform both sampling and density estimation when we have high dimensional data and when we have non-linear transformations. Here are the two distributions that I had taken as an example earlier. F represents the forward transformation that you would need when transforming a sample from a base distribution to sophisticated distribution. So this time around in this slide, I have reversed the placement of the distribution. So this is our simple base distribution, the 2D normal distribution with no covariance, and this is the sophisticated distribution from which we can neither sample nor compute the density. And G represents here the inverse transformation, and you can see that the density computation and adjustment that makes use of inverse function. We talked about it in previous slide as well. That said, I have not yet talked about how these functions look like, and we will do it in next few minutes. But before that, let's see a different arrangement in which you can use this sequence of transformations as well. So this is one arrangement where you have a distribution and then you are plugging in this chain or this sequence of functions and going from simple distribution to a sophisticated distribution and coming back to the base distribution to compute the density. But could we use a similar notion as a component in a bigger model or in a different setup? And that setup, you have seen it already. And this is a setup of variational autoencoder. So now in VAE, one of the primary goal that we have is that we are learning the parameters of the distribution of our latent variables, which are indicated here as mu and sigma z. The assumption, of course, is that the latent variable are following multivariate normal distribution, and hence the usage of mu and sigma in here. We then sample from it, which is so Z is the sample from this multivariate normal distribution, and then we feed it to our decoder. The decoder also outputs the parameters of the distribution, which is also assumed to be normal here. So the decoder is going to output what is supposed to be the recreation of X, and hence it's a distribution of your data, the observed variables. Clearly, the assumption of latent variables distribution as well as the observed variable distribution, that is X, being multivariate normal is quite restricting, but helpful because it is easy to do sampling and density estimation when you have this assumption. So we are now going to see, can we use normalizing flows in this? And here we have the remedy. So interestingly, we do not change anything in our setup until here. We still have the Z that is a sample from the multivariate normal. But what we do now is that we take this sample and feed it to our sequence of transformations, sequence of normalizing flows, and we get Z, which appears to have come from a very sophisticated distribution. The sophistication, of course, depends on how many number of functions you have in your sequence, in your normalizing flows composition chain, and also how sophisticated each individual function is. Now, I have not shown you this in this picture, but the same strategy can be used for x as well, that is the observed variable. It is not necessarily restricted to applying it to the latent variable. And now we are at a point to complete our definition of normalizing flows. The modification is quite simple. You can see it highlighted in the yellow part. All I have done is added few words. So again, one more time, a normalizing flow is a transformation of a simple probability distribution into a more complex distribution by using a sequence of invertible and differential mappings. The next question to worry about is, how do we even define these mappings? Is there any recommendation? Is there any order? Am I supposed to invent a new mapping? Are these mappings neural networks? These are all legit questions and thoughts, and I'm glad you're thinking in this direction if you are. And indeed, this is one of the main areas where the research in this context of normalizing flows happen. So you do already have flows, quite many of them, that researchers have produced. So you could just take those flows and stack them together and learn the parameters of those functions. So the function, remember, the function is supposed to be invertible, but the parameters of that analytically invertible function can be learned using the neural network, or rather we should say that they can be learned using the optimization techniques. And this is what brings us to this question: how do we learn this kind of a model? Well, learning here translates to the parameters of sequence of normalizing flow functions. And the answer is quite simple. We use modern machine learning based optimization techniques. If it comes to the fact that normalizing flows are being used as a component in a bigger model, then you let the optimization technique help you out there as well. So in both cases, you end up using your traditional optimization techniques based on gradient descent. The moment I mentioned optimization techniques, you should think that there is a loss function involved. And indeed, it is no different here. There are two primary choices here. The first one is the canonical way of learning parameters of a distribution or a density function. That is by doing maximum log likelihood estimation. And the second one is KL divergence. So you would use MLE or maximum log likelihood estimation if you do not know the distribution of your data set. You simply split up your data set into mini batches and optimize the parameters of various flows or the functions in your flow using the negative log likelihood. The goal is to obtain the lowest value of the negative log likelihood. Other function, the loss function, could be KL divergence. So KL divergence is a way of comparing two distributions. Now, if you want to compare two distributions, you need to know the density functions of these two distributions. Now, in this case, you would need to then know the density function of your data set or the distribution function of your data set. So you may start to wonder, if I already know the density function of my data set, why do I need to learn it again? Well, you may still be interested in learning that, because the generative model that you are learning would be doing sampling, which means that your target distribution, your sophisticated distribution is so difficult that even though you know the probability distribution function or the density function, you do not necessarily know how to sample from it. And this is where the normalizing flows would come and help you out, because they would help you learn the transformation function such that all you have to do is you just sample from a base distribution like standard normal and then pass it through this sequence of transformation, the normalizing flow, and the sample would look like as if it came from that sophisticated target distribution. The process remains still the same. You essentially divide up your data set into mini batches, and then you minimize the KL divergence and you run your optimization loop as you generally do. I had started this tutorial with two problems, and normalizing flows does seem to provide an interesting solution to both of them. But like any technology or method, it is not the silver bullet. It has its limitations as well, and you have seen them already. But let me still mention them explicitly so that we do not forget. The first one is that the normalizing flows are possible only when you have invertible mappings. And this means that these needs to be designed carefully. There are some building blocks and flows already in use, and then you as a user can stack the ones that are already in use. But if you are interested in creating your own, this is something that you need to worry about. And depending on your mapping function, the calculation of the determinant may be problematic. So this is another thing that you have to worry about. There is another thing that I wanted to mention is that not all normalizing flows are created equal. What this means is that some normalizing flows are good at sampling, while some are good at density estimation. Let me show you some papers, some famous papers on normalizing flow as well. The first one is titled Variational Inference with Normalizing Flows, and it is the paper that sort of jump started this field of normalizing flows in the context of deep learning. I must tell you that this paper did not invent normalizing flows. It did not even invent the terminology normalizing flow. So normalizing flow is a older concept, a relatively older concept, but this is a paper that made it famous in the context of deep learning, and especially in the context of variational inference. They propose two flows. One flow is called planar flow, and the second flow is called radial flow. And both of these flows are not in use a lot. And the primary reason for that is that first of all, they are good only for sampling, not good at all for the density estimation. The second issue is that they are not very expressive, meaning that they are not good at learning a sophisticated sequence of functions. If you want to do that, you will have to unfortunately stack quite many planar and radial flows in your normalizing flow composition. The second one is from Kingma et al. So Kingma and Max Welling, these are the inventors of variational autoencoder, and they proposed in 2017 a flow called inverse autoregressive flow, which found its usage in variational autoencoder. Again, as you can see that this paper also is trying to solve the challenges associated with variational inference. And as we discussed, most of the time when you are doing variational inference, whether you're using variational autoencoder or not, you end up having an assumption of the distribution which is simpler distribution. So the motivation here is that could we use the simpler distribution for doing the sampling and density estimation, but still plug in the normalizing flow so that we still have the possibility of getting a sophisticated distribution. So this particular normalizing flow is very good at sampling, but it is not good at all at density estimation. And the next year in 2018, a new flow was invented called masked autoregressive flow. So the previous one was inverse autoregressive flow. This one is masked autoregressive flow. And this one is very good at density estimation, but it is not good at all at the sampling. And this sort of attests to what I was saying earlier, is that not all normalizing flows are created equal. So if you have an application where your primary use case is to do sampling, inverse autoregressive is a good choice. If you are building a model where you want a exact, proper, fast density estimation, MAST autoregressive flow is a good choice. There is another one which is called density estimation using real NVP. It is quite famous, and it is decent at doing both of them, both sampling as well as the density estimation. There are some new ones which are based on the notion of splines. So one of them is called neural spline flow, and it some of the elements of it are being used in other flows. Essentially, the other papers are building on top of what this paper teaches us. And finally, the one that I had used for the first slide in this tutorial, the pictures for the first slide in this tutorial came from this model, GLOW. So as you know that when it comes to the synthetic image generation for human faces, the GANs are quite famous. The other type of models, they have not been that good at generating synthetic images of human beings, and whenever they have generated, the quality was not necessarily that great, at least not as good as comparison to GANs. And this is one of the first ones which is not a GAN model, it's a normalizing flow model, and the quality of the images that it generates is pretty good. And this, so you have already seen the images in this tutorial, the very first slide. And we are at the end of our tutorial. But before I end it, I wanted to leave you with some more resources where you can go and learn more about normalizing flow. The first resource that I'm recommending here are the blog posts from a gentleman named Eric Zhang. These blog posts were published in 2018, and quite many people have benefited from them, including myself. So this would be my first recommendation. The second recommendation is about the survey papers. So there are two of them published in 2019. One should anyway read survey papers because they help you see the direction in which the research is headed for a given subject, for a given topic. And these two do justice to that, as well as they provide you necessary good background on normalizing flow. And finally, last but not the least, is this recommendation for the GitHub repository. So this is an awesome repository where there are links to various papers that have been published in recent years on normalizing flows, as well as it has links to various code repositories where you would find the libraries and the toolkits that you can use to build your normalizing flow models. The one for the TensorFlow, if you use TensorFlow as your deep learning library, then I would recommend TensorFlow Probability, which has the implementation for many normalizing flow papers, as well as the foundation and building block for you to invent your new normalizing flow. For the PyTorch people, there is a library called Pyro. It's a fantastic library again. And there you have also the implementation of quite many normalizing flow papers, as well as the foundations to build your own. There is there are a lot of links to the third framework called JAX. So JAX is a new library in the machine learning area from Google, which is getting quite a traction, and there are many toolkits that are being written where the normalizing flows are being implemented as well. So if you use JAX, then you may want to check those out. So this repository provides the link to all these things. And that is all. So I wanted to thank you for the time that you spent here with this tutorial, going through this tutorial. And if you have any questions, doubt, queries, please do write in the comments, and I would try my best to answer them. With that said, thank you again and have a good day. Bye.